Hello, everybody. We're looking at Kepler's laws today. Uh, it's the last section of the physics, unit 6, planetary motion unit. All right. So our learning goal is to use Kepler's 3 laws to predict the orbital motion of celestial bodies. Use Kepler's 3 laws to effectively determine an orbital period, frequency, or radius. It's basically our goal for this lesson. Our first law is all planets move around the sun in an elliptical path, with the sun at one of the 2 focal points of the ellipse. And so I'm going to make some sort of exaggerated ellipse here, okay? And ellipses at basically 2 focal points, and excuse me, the sun is in one of these, okay, and the other location right there is empty. There's nothing there. And what ends up happening is the planet ends up moving around like that, okay? Now, one of the definitions, bonus little information, definition of an ellipse is that this plus this, those two distances, is equal to this plus this, right? Or, this plus this. Essentially, that's the definition of an ellipse, is that all points on the ellipse are the same distance away from the sum of the distances from as the sum of the distances from the foci. Okay, that's our thing. That's Kepler's first law. There's not much math to it, besides the fact that it's just basically a simple statement saying that planets move in an ellipse. It was a big deal back in the day because everybody else thought everything moved in a circle. And so when this guy Kepler came along and said, no, sorry, it's an ellipse, verified that it was an ellipse, the other people probably sort of thought about it beforehand. I'm not exactly sure if it was the very first one. But anyway, it was a big deal. Second law, a straight line joining a planet and the sun sweeps out equal areas in equal intervals of time. This one I love. Actually, this is pretty cool. Cool repercussion, or cool law that this guy discovered. Basically, if I've got a planet and I'm moving around, anyways, that kind. I got a planet and I'm moving maybe from here to here, right? If I draw a line here, and I draw a line here, and I figure out this area, okay? And then I've got maybe a planet here, okay? Now if I draw a line like that, maybe my planet's there, and then I draw a line like that, such that these two areas, this area here, and this previous area that I drew before, so those two areas are equal. If they are equal, I don't know if they're equal in my diagram, but maybe it would have to be here, I'm guessing, or something like that. Maybe these two areas are equal, this one and this one. All right. Then, if those two areas are equal, then the time that it takes for the planet to move from here to here is the same as the time that it takes for the planet to move from there to there. Okay? If area 1 equals area 2. Okay? This is area 1. That's up area 2. And this is area 1. Okay. Anyway, I do like that law. It's kind of fun. And finally, the cube of the average radius of a planet's orbit is proportional to the square of its period. And my formula came out a little incorrectly again, so it's r to the third fish t squared. Okay? And you might say, well, what the heck is fish? Fish is means is proportional to. Okay, and basically it can be replaced with a hang on a second, let me and then basically what that means is you can replace the fish with an equal sign, and you can multiply one of these two things by some sort of constant, right? Meaning that they sort of maintain a ratio. Now, the constant that they use isn't K, they actually have to use a C for this particular topic, okay? So, essentially what you end up getting is this C value is R to the third over period squared. And how does that pan out? It basically just means that for the sun, for example, every planet or even every piece of dust or like anything, satellite or whatever, asteroid, excuse me, that rotates around the sun, if it's trapped in an orbit, and if it's in a successful orbit, then the average distance from the sun, which is r, okay, which is r, and the period with which it takes to complete a revolution, they respect this ratio, right? Obviously, cubed though and squared, right? So that's basically Kepler's third law, right? So let me just do a quick drawing of that. I've got the sun, and I've got two things that rotate around it, okay? Here, this object here, the average radius would be sort of, if I were to draw a bunch of radii, right, and I were to average them out, I would get the average radius, okay? Then the period it takes for it to rotate around one full time, it should follow this pattern here. Right? That's for one particular object A, we'll call it. Anyway, it turns out that object B should also follow this pattern as well. Okay, and object B would be maybe this guy here. So its average radius, the average of all these radii, and its period of rotation follow the same ratio. Meaning, essentially, the larger the radius, the longer it takes for it to, rotate around. Okay? So let's put this into some practice. In example 5 here, the average Earth orbital radius is given, okay? And that's an 8 right there, if you can't really see it. It's an 8 times 10 to the 8, 125 times 10 to the 8 kilometers. And the period is about a year, it's 365 days, give or take. and use the Earth's average orbit or end period to find the sun's constant of proportionality, right? Yeah, so that's actually what they're calling this thing in our textbook. It's called the constant of proportionality for the sun, and they usually give a little subscript for this, depending on what you're talking about. The Earth has its own constant of proportionality, and all things that rotate around the Earth obey that rule, and then so forth. Everything has these values here. Okay. Let's figure out the sun still, right? So basically, if you want to figure out the sun's constant of proportionality, you got to get some kind of object that rotates around the sun. Well, the Earth does, so that's fine. And you calculate it, you figure this out. So the constant of proportionality for the sun is equal to the average radius of the Earth, Q, divided by the average period of the Earth squared. Okay? And, well, everything needs to be in meters and seconds as tradition holds. And so we're talking about 1.5 times 10 to the 8, 9, 10, 11 meters, right? This 8, but then that's in kilometers. So if you want to click it over into meters, you're going to go ahead and have to do it like that. So that's a square. Then we got 365.26 days. I got to figure out how many seconds are in a meter. Just got to calculate that out. Which will, where I put my calculator. So I'm going to multiply 365.26. I'm going to multiply it by how many days. It's already in days, so I got to get it into hours. So I got to multiply it by 24. So 365.26 times 24 times, that puts it into hours. Now I multiply it by 60, that puts it into seconds. And then, minutes. I'm going to multiply it by another 60, puts it into seconds. Oh my, such a large number. It's 31,558,464. That's a mouthful. So it's going to be 3, 1, 5, 5, 8, 4, 6, 4. So that's a bit dark in here, so I'm just having trouble seeing that. That's a square. Oop, this one is supposed to be to the third. And you basically sort of calculate all this out, and you get some sort of value. This is the constant of proportionality for the sun. I'm going to pause that and make sure I plug this in the calculator properly. All right, so there you go. We're getting about a 3.4 times 10 to the 21. Okay. Units on that, by the way, are meters cubed per second squared, which makes perfect sense because these would be in meters and these are in seconds. I forgot to write here. Seconds. Okay. Anyway, there it is. That's our constant of proportionality. An asteroid has a period around the sun of 50 years. Find the average orbital radius. Ah, interesting. So since it's around the sun, we know that the period is 50 years. Okay, usually they use an A for years, which stands for anno, I suppose, Italian, or Latin, I guess. And then basically what I want to find is the average orbital radius of this thing. And so essentially what I'm going to do is I'm going to solve for it using a little bit of algebra, and we all like algebra, and so it's the constant proportionality of the sun times 50 years squared should equal the average orbital radius, third root, all that side. And that's basically how we're going to get the average orbital radius. Okay, right? And we'll basically kind of just take this constant of proportionality, throw it in there, and then don't forget, we have to change this into seconds. And your answer would be in meters. It's more or less a quick run through of Kepler's laws. Let me know if you have any questions.